Hi, today we're going to learn how to do the electrocardiography lab. There are five basic properties of heart cells. They are excitable, so it means that they can reach threshold and respond to impulses on their own. These guys are a little bit different than action potentials of nervous and skeletal muscle, and we'll talk about that in lecture more. They're autorhythmic, so they can generate an impulse on their own. So they autorhythmically and continuously generate action potentials, and then they propagate those to other cells or other cardiac cells in the body. They contract, and then they have a refractoriness, which means they have a really long absolute refractory period, so that they can't be stimulated again to produce an action potential. So they're different than skeletal muscles. Since we're not able to do this physically in lab, I wanted you guys to look at the virtual EKG lab at McGill University and see how they did the setup and the introduction of those in the experiments. The conduction pathway of the heart is SA node, right? So this is something that you learned in 260 if you took 260. Otherwise, this is something that you learned that we talked about in 251 already. Okay, so let me actually get a colored pen. Let's see if this works. Okay, so the conduction pathway for an action potential. So we have bundles of pacemaker cells in our heart. These pacemaker cells are cardiac cells or modified cardiac cells that generate action potentials. So these pacemaker cells only generate action potentials. They don't contract. They don't have actin or myosin in them to contract. Okay, so the first bundle that depolarizes is your sinoatrial node. Let's see if I can actually write this. Your nope, can't do it. Sorry, guys. Your sinoatrial node. So this depolarizes, and then once it does, it's going to spread through the atria, through those contractile cells. Remember, all of the contractile cells are in the myocardium, and then it's going to go to the atrioventricular node. On an exam, when you're identifying these, please write them out. So don't abbreviate AV node. It's actually atrioventricular node. And then it goes to the bundle of His, right? And then it goes to the right and left bundle branches, and then the right and left Purkinje fibers. So which portion depolarizes first? The SA node spreads that action potential through the atria, and then it goes to the AV node. And then the AV node spreads it through the ventricles. So it's going to spread it down the interventricular septum, down to the apex, and then up the sides. And so this flow of electrical current causes the atria to contract from the top down, and the ventricles contract from the bottom up. These guys are electrically isolated. So when you're looking at the anatomy, you learned that the myocardium wraps around the atria in a figure 8, and then it's sort of a curl shape or spindle shaped for the ventricles. And so the impulse can't go down the outside of the heart because these guys are electrically isolated from one another. So the connection port is the AV node. Okay, let's move to the next one. You can read this on your own. So typically, the SA node is the node that depolarizes the fastest. It depolarizes at a rate about 60 to 100 action potentials per minute. Notice that electrical events have to happen before mechanical events. So you have to have that SA node generating an impulse, and whatever that action potential rate is, that's going to align with, or that's going to cause that many beats per minute. If the AV node is damaged, or if it discharges more slowly, the SA node, the AV node will actually take over. So the AV node depolarizes at a rate of about 40 to 60 action potentials per minute, which actually can sustain cardiac output. If the AV node and the SA node are damaged, the bundle branches can take over, but the bundle of His or the bundle branches or Purkinje can take over. Their action potential rate is about 20 to 40 beats or action potentials per minute, which can sustain life for a little bit. Sometimes those, sometimes your cardiac cells get irritated, whether if you're sick or dehydrated, then you can produce random action potentials. Or sometimes you can generate an action potential irregularly, and that's going to result in a premature beat. And you can read that on your own. Let's see. So mechanics of the electrocardiogram, if we were doing this in lab, we would hook up the electrodes. So you would have a negative electrode on the right arm, an electrode on the left arm, an electrode on the left leg, and an electrode on the right leg. The right arm is where your negative is. The left arm is where your positive is. For lead 2, negative is right arm, positive is left leg. So you're taking a picture electrically what's happening in this direction. And then for lead 3, your negative is left arm, your positive is left leg. And so that's your lead 3. We're interested in lead 2 because this captures a mean electrical axis of the heart. Remember, your heart sits in your mediastinal or mediastinum region. It's about the size of your fist, and it sits a little bit tilted to the left. And so that interventricular septum is where most of the electrical current flows through. And so lead 2 is the great lead to capture all that. So we're going to evaluate lead 2. We're not doing the augmented leads or the chest leads. What I recommend if you're going on to your professional programs, take an EKG short course so that you learn how to interpret EKGs and rhythms. Okay, so here is the recording. Take a look at the measurements. So this is an EKG strip. This is a typical EKG strip. And if you notice, I just forgot what I was going to say, sorry. If you notice, or I want you guys to pay attention to the axes, okay? So number 1 here, axes. Your vertical axis is amplitude. Each box is 0.5 millivolts or 5 millimeters. Horizontal axis is time in seconds. Each box is 0.2 seconds, and each itty bitty or small box is 0.04. Okay, so take a look at this box. So this box right here on the left bottom of the EKG strip, we're going to blow that up, or the top right, I guess, would be more appropriate. We're going to blow that up. Take a look at this. So I'm not too interested in you knowing the amplitude, but I am interested in the time, okay, the time duration. So one box is 0.2 seconds in the horizontal axis or the x-axis, right? And each itty bitty box is how much? It's 0.04 seconds, okay? That's important because you're going to be measuring how long each of those take, right? Or how long each of the waveforms take. Okay, so let's look at the EKG. The waves that I want you to know and the intervals that I want you to know are listed below, okay? So here's a typical EKG, so let me go through with you. Here is your P wave, your QRS, and your T wave. And then typically you don't see a U, skip over that, and then this is your second P wave in your QRS and T, right? What does the P wave represent? The P wave represents atrial depolarization. Where am I getting that from? See number 1 for waves, intervals, and segments. A, P wave represents atrial depolarization, okay? So P wave is atrial depolarization. Your QRS represents ventricular depolarization. That's letter C. And then your T wave represents ventricular repolarization. And then we have another P wave after that, right? Let's take a look at a couple of intervals. So some of the intervals that you have to measure are the PR interval. So the PR interval is from the start of P to the start of Q. Why do we call it a PR interval? We use intervals when we have a waveform in the measurement. Segments are when there is no waveform in the measurement, or when we're doing between the waveforms. Okay, so here's a PR interval. Why do we call it PR? Because sometimes you can't see the Q, it's at start of Q. Unless you can't see it, it's at the start of R. Then we have the QRS interval, which is QRS, shows the ventricles. And then we have the T wave. Also, if you go down to, H, the PT interval represents systole. So PT interval is start of P to start of T, right? That's PT interval, and that represents systole. Systole is when your heart is contracting, and then T to P segment is when the heart's at rest, so that's diastole, right? So we'll come back to this page. Let's skip this page for a second. For the lab, what you would have done is you would have taken a resting EKG on one of your group members, and then you would have had them exercise for a couple minutes and come back and take a post-exercise EKG. So I have put those in here for you guys. So what I want you to do on the resting EKG and the post, let's see, I guess I just have it resting. You can label both of them for practice. So I want you to label the voltage of 0.5 millivolts on each of those. I want you to label the time intervals, and then I want you to label all of these EKG events, okay? This is worth 4 points, so spend some time on this. Print it out and label them. So if you notice, if you look at the resting EKG, there's a line that's denoting 0. So then we move the cursor over. That line is 0.2, 0.4, 0.6, 0.8, 1 second. 0.2, 0.4, 0.6, 0.8, 2 seconds. 2, 4, 6, 8, 3 seconds. Okay, so this is 3 seconds worth of data. And then you can do the same thing. So label the post-exercise 3 seconds worth of data. I tried to get them the same size. I took them from different places, but it's pretty close, okay? 0.04 then, do you see these itty bitty boxes in here? Each one of those itty bitties is 0.04, okay? The P wave, so let me show you where the P wave is for this one. So here's your P wave for your resting, your QRS, and then your T wave is right there. Then the next P, QRST, P, QRST. Label those, so label all of your events, ventricle depolarization, ventricle repolarization, atrial depolarization, systole and diastole, right? So before you move on to measuring them, I want you to label everything on the resting and post-exercise EKG, okay? Then let's go up to the top, all right? So for the cardinal rules for interpreting dysrhythms, actually we'll go right here. When you're looking at an EKG, you're going to be evaluating resting EKGs, right? And patients. The first thing that you're looking for is that the rhythm should be regular. What does this mean? You're going to look at the time span. You don't have to actually measure the time span, but you're going to look at the time span from 1 hour to the next hour. And the time span should be the same, okay? You can do this with the caliper. So you can stick the caliper, one of them on an R and then the next one on the other R, and then keep moving it through the R to R intervals. Or you can take an index card. For this class, you can just eyeball it because obviously we're not clinically doing it. But rhythm should be regular. The heart rate should be 60 to 100 beats per minute. How do we figure that out? You're going to count how many R's there are in 3 seconds and multiply that times 20. because there's 20 3-second intervals in 60 seconds. Or count the number of R's in 6 seconds and multiply that by 10 to figure out the heart rate. So you have to label 6 seconds worth of data, count the R's in that, and then multiply it by 10. Don't have to do the R to R method today. So then the next one that you're going to do is your P to QRS ratio. It should be 1:1. So you're looking for a P wave, and then a QRS should follow it. And then the next P wave, QRS should follow it. The next P wave, the QRS should follow it. If that holds true, then we write that as 1:1. Your PR interval should be less than or equal to 0.2. So 0.2 is one big box. So your PR interval should be one big box or less. And then your QRS interval should be usually it's one itty bitty box. It's 0.04, but it can be 2 itty bitties or a little bit more than that. So it's 0.1 or less. All right, so what I want you to do for this is I want you to label everything on resting and post-exercise EKG first. Then I want you to use these to fill in the table below. So for rhythm, I filled this one in for you. So rhythm, the resting EKG, the rhythm is regular. Remember, you're looking at your R's, so they're equispaced or equidistance, if you will. And then look at the R's for this one. They're regular as well. Okay, so the rhythm is regular for the resting. The rhythm is regular for post-exercise. Is this normal? Yes, it is. So then the beats per minute, I want you to calculate the beats per minute using the 3-second method. Fill it in for resting and post-exercise. Show your calcs. Do the 6-second method. And then your P wave ratio, measure how long the P wave takes, measure how long the PR takes, QRS takes, T wave, and then TP segment, okay? For 3 and 4, I want you to actually evaluate these. So based on your data table above, are there any differences between resting and post-exercise? I want you to give me what you think. And then for number 4, I want you to list the 5 rules for interpreting EKGs and then evaluate the resting one and give me the values. If you have any questions, let me know. We'll be covering this for lecture as well. So once we get to this for lecture, that should help. I will post this as an assignment, and so I would like you to hand this in. I would like you to upload it to the assignments folder on your Canvas shell so that I can grade it through Canvas. If you have any questions, email me. Otherwise, enjoy evaluating your EKGs.